So from that, can you get the actual moment of the bar, or is that the moment?
No, that's the cross section. The second moment of area related to cross section, nothing else.
So from there,
Just the geometry.
So you
just
can't,
the geometry.
You can't get the moment then.
Moment is then you have to relate that to formula. That sigma is equal to m over I times y. That type.
So it's this one.
That's
That's what's confusing, right? So that's how you actually get the moment then.
Just a quick question. They're on the most recent test. All the answers, I've actually put a negative all the answers was the same answer.
The previous test.
Yeah.
Send me an email.
I sent her a book there.
I normally
I sent it to the wrong one.
replied to everybody.
Might be in the wrong one, I should. Yeah. Is that you?
Yeah. What's your name?
Admister. Yeah,
Just let me check.
no worries.
Analyst. And I have almost everybody I have.
I might. No worries. It's just some questions.
Okay. I'll update it.
Alright, thank you.
You need to test next Friday. What's that?
So that would be the stresses and the deflection.
Stress and deflection.
Yeah.
It's a second moment of area.
Yeah? Okay, we'll make a start now. So today is the last topic that we will be covering, and after that next 2 weeks I will leave for problem solving, any concept that you are not clear about, as well as providing support for your group work if you want to show me that. So I'll discuss how best to support that as well. So we'll discuss that. But in terms of the syllabus and the content, so today hopefully would be the last concept wise. Now of course I need couple of sessions to go through some of the examples on the stress as well as the deflections. So we'll do that next week anyway. So last Monday we started looking at calculations for deflection of beams. So just to bring your memories back, So we used these expressions that curvature is d2y dx2 if a curve is x versus y, where y is the deflection at a distance x. So y is the deflections of this beam, then the curvature is approximated as d2y dx2. Now we use that to relate that to moment, as moment is ei times d2y dx2. So then we took some approach. First we found out at an arbitrary distance x what would be the bending moment m in terms of x, and then once we got that, then we subsequently integrated it to calculate the rotation, which is dy dx, and the deflection, which is y. So we did two problems. One was a simply supported beam under UDL and a cantilever beam under UDL. But often you will find that writing that sort of moment equation is not an easy task, or rather having a single moment equation is not an easy task. For example, if I take you to tutorial 4, now let's take the first one, for example, first problem. You have got an uniformly, you have got a beam and a single point load 5 kilonewton acts at a distance 2 meter. Now if you write the moment equation for this, it will be, which we have got in here, the moment equation should be from, if x is less than 2, that means you are somewhere here, if x is less than 2, you will get moment equations in terms of m is minus 3.6 times x. If x you take more than 2 meter, that is there, then two loads come into the moment equations, the reaction force as well as the load. So the moment equation should be like this. So what you can do is you can integrate it section by section. So you have got moment equation m is minus 3.6 over this distance. So you could integrate using those expressions there, and then you have it another way there. Now that is just for one load. Now what about if the problem is little bit complicated with more than one load? Say for example here. So you have got UDL, a point load, and then there, and all sorts of. So if I look at solution for 2b, so solution for 2b will have, so this is solution 2a, and solution for 2b, you could see that x less than 4 meter, x between 4 to 8 meter, x greater than 8 meter, all different moment equations. So that makes, then you have to do integrate each one and then applying the boundary conditions. And then the boundary condition, because all of these integrations will result in integrating constants a, b, c, d, etc. So satisfying those for each part is not a trivial exercise. So to address cases like this, what I am going to do is introduce to you a concept called unit step function. Now what is unit step function? So you will possibly learn that later in your maths if you haven't done that yet. So unit step function is a functions like this. So if you draw, let's say x along this, and then y is unit step function, sometimes also called a delta function or heaviside function as well. So if a function is such that it will have values of 1 after some point, something like this. So this value is 1, for example, and say this is a I don't know, maybe a. So this is a unit step function x minus a with a unit step function, say delta. What that does mean is that if x is less than a, then this function y would be 0. And then this would have only values if x is greater than y, then it will have got y equal to 1. So this is unit step function. So we'll be using this in a slightly different way. So multiplying the load and everything else. Now instead of using any other symbol, like some people use the heavy side functions like h, x minus a, etc. Lot of different symbols people can use from a mathematical point of view. But what we will do instead, we'll use something called Macaulay bracket. So these are the engineer's way of treating unit step function. So instead of having rounded brackets, we use pointed brackets. And this is exactly the same as unit step function. So if you get functions like this, this means that this will be equal to 0 if x is less than a. So that means it doesn't allow any negative value. So it does not allow any negative value. So any negative value if you get, then that means it is 0. So instead of a negative value, you put it 0. And this would be equal to the standard x minus a if x is greater than a or greater than equal to a. So it will be 0 and fine. Now the beauty of approaching this way is you can use all other integration and differentiation sign as normal. So we'll use this unit step function in this disguise, and this is called heavy side as well. So heavy side function as well, it is called, or unit step function. So unit step function. But from the structural engineering point of view, we'll use something called Macaulay's brackets. So Macaulay's brackets are like these pointed brackets, so that means it will not allow any negative values in there. So if you see any of these, that means it's only 0 or positive. So that's what we'll use. And how we are going to use? We are going to show you with some example. So possibly we'll take up this example as the first one, and then we'll do that subsequently. Now in terms of, no, this should be plus. Okay. In terms of the differentiation and integration, it's exactly the same way. So in Macaulay's bracket, if you do differentiation, you get differentiation of Macaulay's brackets gives you exactly the same as you have n times x minus a to the power n minus 1, and integration is also exactly same way as the rounded brackets would do. Now let's look at, first of all, before doing this problem, let's do it with another problem. Say if I want to find out using Macaulay's method what are the bending moments expressions under this case. So the bending moment for this case would be, let me show the solution for that. So the reaction force is 3.6 kilonewton and 1.4 kilonewton in this case. 3.6 kilonewton and 1.4 kilonewton. So if I want to write moment expressions, so the moment expression, let's say x is between 3.6 and 5. So x is here. So the moment at a distance x would be 3.6 times x. And of course, our sign convention for moment is as follows. So the moment is, hogging moment is positive. So that means left hand side anti-clockwise moment positive, and this is giving left hand side as a clockwise moment. So this is a sagging moment, so that should come with a negative sign. So minus 3.6x. Now make sure that you understand that, and as I said before, sign convention, you can use anything as long as you are consistent. So minus 3.6x is here. Now what happens if I come to here, if x is beyond 2 meter? Now what I can see is that 5 kilonewton only will be applicable in the moment equation if x is more than 2 meter. So what is the moment due to 5 kilonewton? 5 kilonewton moment would be, now if this distance is x, so imagine this distance is x from here to here. So this distance is x, let's put it that way. So the moment due to 5 kilonewton is 5 times x minus 2, because this is the distance that would be I will be interested in. So this distance is x minus 2 meter, because that distance is 2 meter. So the moment due to 5 kilonewton would be 5 times x minus 2. So that would be the moment due to 5 kilonewton. Now that is creating a moment in the anti-clockwise direction, or a hogging moment. So that would be with a plus sign. But to make it a general expression, we will not use a rounded bracket. We will use a pointed bracket or a maculus bracket. So that is the expressions of the moment. So that means x 3.6 kilonewton would be for any x starting from left to right, but 5 kilonewton will kick in when x is more than 2 meter, and then that moment is 5 times x minus 2. And once I have got that, then I can run my analysis. So I can put that this is as EI d2y dx2 is this moment minus 3.x plus 5 times x minus 2. And I can then integrate it twice. So first integrations give me the slope. So that would be minus 3.6 x square over 2. That would be the integration. And this one I'll be exactly get this expression as 2 square over 2 plus integrating constant a. I can then subsequently do another integration to get the displacement, would be minus 3.6. X square integration would be x cube divided by 3. So 2 times 3 is 6. Then similarly 5 x minus 2 square integration would be x minus 2 cube over 6 plus ax plus b. Now that's it. A and b I can find out from this known boundary condition. So at x equal to 0, y equal to 0. So that means now you have to be careful. At x equal to 0, y equal to 0 means I am going to put in the value here, 0 is equal to, now this is 0 if I put x equal to 0. And this is 0 anyway, because this is not 0 minus 2 cube. Because this is value, if x is less than 2, there is almost this, you can think of a switch. That if there is any negative value there, the switch is off. So that will not output any value at all. So this would be, second value would be 0 anyway, because x is less than 2. So that would be 0. And then a times 0 and plus b. So first equation will give you b equal to 0. And then you also know that at x equal to 7 meter, I've got another support. So the displacement is 0. So at x equal to 7 meter, my displacement is 0. So you'll get, again, this is 0. So 7 meter means minus 3.6. 7 meter means 7 cube over 6 plus 5 times. Now 7 minus 2 is positive. So 5. Yes, I can use that now. So 5 times 5 cube over 6 plus a times 7. So this will give me the value of a. So once I know value of a, I can go back to these expressions and draw my diagram. And while drawing the diagram, I need to be careful that I don't include any value here if it is x is less than 2. When x is more than 2, then this would be a normal bracket. So for x less than 2, this quantity will give 0 value, because this maculus bracket is not switched on at that point. So that will give us 0 value. So that's it really, and then you can carry on doing lots of different problems accordingly using this method. So let me go back to the lecture notes. and complete the solutions that we have there. So this is 4. Okay, so this is the expression, this is the problem that in the lecture notes we have. We have got a point load at the middle. So point load at the middle W, and then L over 2 and L over 2. So the reaction force in this case would be, here would be half of that load, so W over 2, and half of that load would be W over 2. So what is the moment? Now the moment at a distance x, let's say here. So if I take a moment at this stage, so moment at a distance x is here, that would be W over 2 times x. Now that is going to create a sagging moment, so in a left hand side clockwise. So if this beam part is there, then the effect of that load is to create a moment like this. So that means it is, if you hold on to this side, then that will create a sagging moment. So that is a negative according to our convention. So that is a negative moment. Now if x is more than L over 2, let's say x is here, then I have got W and it is creating a clockwise moment, so which is a hogging moment. So W times, but this is only valid if x is more than L over 2. So W times XL over 2, so with a plus sign. So that's the moment expressions in this case. So W times x minus L over 2 with Macquarie's bracket. And we import that with our d2y dx2 is Wx over L over 2 minus Wx over 2. Just rearranging this, putting the first term in over there. And integrate it once, it would be W over 2x square, etc. with an integrating constant a. And similarly integrating it once more, you will get the deflection. So this y is nothing but how this will deflect. So y is the profile of deflection. So y is the profile of deflection. So y is the deflection profile. So deflection profile, so any values of x if you put, y will give you the displacement at that point. If you put x equal to L over 2 in this expression, then that will give you displacement at the midspan. Similarly, if you put x as quarter, then that will give you displacement at the quarter span. 3 over L over 4, it will give you displacement at this point, etc. Now you can also see at left hand support, at x equal to 0, y is 0, because displacement is 0 at that point. So if you do that, that will give you B. Similarly, at x equal to L, which is the other end, the displacement is 0. So if you do that, that will give you A. So that will give you A. So with a bit of algebra, you will find out A. Once you get that, then you can find out the dy dx as well as x. So dy dx is nothing but the slope. So the slope is dy dx. The slope is dy dx. So dy dx is the slope, or gradient, you can call it, gradient of the deflected profile. So dy dx is slope or the gradient. So once you get that, then you get the deflections profile, and at midspan you can find by putting x equal to L over 2, and maximum deflection is this in the case of a beam with a point load in the middle. And at the support, the slope is maximum, so the slope or the gradient is maximum here and here. So you can put in the gradient expression x equal to 0, and this will find the gradient. So in this example, the crucial step was to apply the boundary conditions correctly. Now that is true. Now I'll show you few other cases just to check whether you can appreciate the boundary conditions correctly. Let's say I have got a beam which is like this. And let's say this is L. And as usual, I'll take x is the horizontal directions from the left, so this is x, and this is y, let's say, vertically downward is y. Can you tell me what are the boundary conditions in this case? So can I say at x equal to 0, y equal to 0? That means deflection is 0. Because if this beam deflects, this beam will deflect in this way. If the load is something like this, for example, or any load downwards, then it will if the load is upward, of course it will deflect upward, but at the support means there will be no deflection. So at x equal to 0, y equal to 0. And the other one you can do at x equal to L, which is at this point, y equal to 0. Now, what about this beam? If I have a cantilever beam, and as before you could do x is along that direction and y is along that direction, and you have got some load acting onto it like this. So what do you think the boundary conditions should be? So what is the boundary condition? You almost require two boundary conditions for these cases. So what would be the known conditions? So what will be the known conditions? So how this will deflect? So this is fixed point. So that means slope here is 0. Because the fixed condition means it will not allow it to rotate. So there would be a bending moment generated in this point as a result of it. So any obstruction or any constraint to movement will create reaction. So here there was a constraint towards the movement in terms of the translation in the vertical direction. So a vertical force, reaction force was generated. But there was no restraint against rotation. So no moment is generated at that point. And exactly similar here, this roller will restrict vertical movement, so vertical reaction will take place, but not any moment. Here, the fixed support doesn't allow any rotation. So the rotation is 0, and this might go like this way. So rotation is 0, as well as the displacement is 0. So that means you would expect a vertical reaction force, because this doesn't allow any vertical movement, as well as it doesn't allow any rotations, you would expect a reactions moment in here. So these are reaction force and moment. So reaction force and reaction moment, because reaction force develops because the vertical displacement is 0. And reaction moment develops because the rotation is 0 at this point. So your boundary conditions you can write at x equal to 0, the displacement is 0, because this doesn't allow to move up or down. And at x equal to 0, dy dx is 0. So that means that the rotation is 0 at this point as well. Okay. Now, if you have a different problem, let's say I have got something like this, and let's say it has got okay, and let's say you start x from this point and y along that direction. And let's say, let me give you the thingy, let's say this is L1, let's say L2, and let's say L3. And let's say you have got certain loads acting in this way. Can you now tell me what would be the boundary condition if I solve this one? Yeah? At x equal to L1, at x equal to L1, y equal to 0. Very good. And another one? At x equal to L1 plus L2, y equal to 0. So that is absolutely perfect. So what you need to know these known conditions to get those integrating constants. And once you get that, then absolutely using this is almost a mechanical process that you find the load and then you find the other quantities accordingly. Is this clear so far? Yeah.
Wait, so how do I do it for multiple supports like this? So it's just two poly brackets beside each other?
You start with x, and whenever the load is coming, okay, let's devise a problem and then show it to you how to do that. Okay, so you want exactly the similar problem? Okay, I don't know whether I've got any problem like this, probably not, but let me devise a problem like this. Okay, you have got a beam like this, and one side is pinned, another side is roller. Any suggestions for the length? 2 meter, okay. 5. And this one? 3. What? 3? 3, okay. So maybe I need to make it a little bit bigger, 3 meter. Okay, any idea about the load? What sort of load you want to put in? So here UDL, let's put on the midspan some UDL. Any values? 10 kilonewton per meter. Okay, any point load in the end, maybe? How much? 50 kilonewton. Any point load in this span? Slanted is just take a horizontal component. Don't make too complicated, okay? Huh? Triangular load. That would be good. Okay, keep the triangular load for the time being. Otherwise you will be here. One example, one question I gave by mistake on this last quiz and you made a mess of it anyway. So let's keep the triangular load for the time being. We'll come to that. So another load, let's say at 1 meter distance. Let's say another 1 meter distance, another load. How much this one would be? 19 is too mean a number. 20 is better. Okay. 20 kilonewton. Okay. So let's say I want to find the deflections of this pin. That's my motto. So first thing I will do, I need the reaction forces. Without the reaction forces, I cannot carry out this problem. So first thing I will do is I'll find the reaction forces. So put the loads on them. And then I need the reaction forces. So let's put my reaction forces here as R1 and R2. These two would be the reaction forces. So how do I find the reaction forces? These two reaction forces. So first step, I need to find these reaction forces. How do I find that? Moment. So I can take a moment about this point. Let's say this point is point A. So I take a moment about point A and set it to 0. So what I have got, and doing this moment equilibrium equation, I can choose a sign convention which is either clockwise moment or anti-clockwise moment is positive. It is not the bending moment sign convention. You must make sure that the hogging moment positive or sagging moment positive, that they are primarily for the bending moment sign convention because they come in pair, left side and the right side of a cross section. Here I am calculating equilibrium of all the forces. So let's say I take bending moment as clockwise as positive. Let's say this is my sign convention. So 50 kilonewton moment about this point is creating clockwise moment or anti-clockwise moment? Anti-clockwise moment. And what would be the value of the moment? That would be 50 times 2, and that is an anti-clockwise moment, so I put it as a negative value. What about this 10 kilonewton per meter? So the way to deal with this is to find out what is the total load of this UDL. Whenever you have got this distributed load, be that uniformly distributed or triangular or parabolic, any form of distributed load, first find out what is the total load and then find out where do you think the centroid of that load is, because that's where we'll calculate the moment about. So what is the total load? 10 kilonewton per meter means it is 50 kilonewton. So 50 kilonewton, this is uniformly distributed load, so you could easily expect that that would probably act at the middle of the cross section, middle of the span. So this whole load, you could say 50 kilonewton, that will act at the middle of this, so at a 2.5 meter distance. So what type of moment that will create, clockwise or anti-clockwise? Clockwise. So I will put 50 times 2.5 is the load due to UDL, and that is the clockwise, so I'll add a plus. What about R2? R2 is another force, so R2 is the reaction force, R2 times 5 is the force, and that is creating about 0.8 anti-clockwise moment, so I'll put it as a negative sign. And finally the 20 kilonewton load, so moment is 20 times the distance from here is 5 plus 1, so 6 meter, and it is creating a clockwise moment about 0.8, so that is a plus, and that's it, that there is no other force, so that equal to 0. So this will give me my R2. So R2 times 5 times R2 would be, so if I take it to the other side, that would be 50 times 200 minus this is 125, and minus this is so minus plus 120. Okay, so that is R2 times 5. So so that would be is 25, so 145. So R2 would be 29 kilonewton. Check the calculation. So probably R2 is 29 kilonewton. So once you have got R2, then you can find out what is R1. So either you can take moment about this point, or you calculate the total load and you find out what is R1. So R1 would be the total load, which is 50, plus that total load 50, plus that other total load 20, minus R2, which is 29 kilonewton. So 120 minus 29, so that would be 91 kilonewton. Okay, so that's the first step we have done. Okay, so provided this calculation is right, now we are ready to write down the moment equation. So let me do this one again. Draw that again. So you have got here as R1 as 91 kilonewton, R2 as 29 kilonewton, and then you have got the load acting here is 50 kilonewton, and this is 10 kilonewton per meter, and then there is a point load of 20 kilonewton. Now you say, okay, as before, I'll take X along that direction, and my Y is from this point. Y is down. So I'll write down the moment expressions. So how do I do that? So first thing is I take a moment at this point. So if I take a moment at just for the 50 kilonewton load in here, so the moment expressions would be, So the moment at a distance, arbitrary distance x would be, so if it is the first thing is up to here, that is 50 times x. Now I am calculating bending moment. So I'll go back to my bending moment sign convention. Bending moment sign convention, if you remember, it is hogging moment as positive. So if the left hand side moment is creating hogging way, then that's a positive. So 50 kilonewton about this point will create a positive moment. So 50 times x. So that would be 50 times x. Now I come to here. So I have got now 50. So now x is this much distance. Now x is, now this is x. This distance is x now. Now this distance is x. So I have now got 3 forces instead of 2, instead of 1. I have got force due to 50. So that would be 50 times x. That would be positive moment about this. I have got 91 kilonewton force, and that would be acting, now this distance is x minus 2 meter. So 91 would be creating a sagging moment, so that would be minus 91 x minus 2. And of course x is here, then that is only valid if x is more than 2. So use Macaulay bracket x minus 2. And also I have got this load now, which is 10 kilonewton per meter, and that is creating sagging hogging moment. So I have to consider this. So what is the total load for this is 10 kilonewton times x minus 2. That's the total load. 10 times x minus 2 is the UDL, and where this will act, that will act half of this x minus 2. So that is x minus 2 over 2. That's the moment due to this little bit of load over here. So let's write it down into our expressions over here. So 50 times x is there, minus 91 times x minus 2, because that is only valid if x is more than 2, plus this one is plus 10 times x minus 2 square over 2. That means this is only valid if x is more than 2. So it will continue like this until I come to this point again. Now this point now, I have got until this point. So if this is x now, all of these previous expressions is valid. So this we have taken care. This we have taken care by the first expression. This we have taken care by the second expression. The UDL I have taken care, but that point UDL has stopped. So this expression means that this UDL is extending beyond this point. So that means there must be, because if I keep that point, that means we have to have UDL going into the opposite direction. And of course there is 29 in there as well. So first let's deal with 29 first. So 29 will act at a distance of this one is a, so that would be 2 meter plus 5 meter, 7 meter. So that would be x minus 7 meter. So x minus 7 meter would be 29, and that will create sagging moment. So let's first write that down. So that would be minus 29 x minus 7 meter. So that is, this 29 kilonewton will only act if x is more than 7. But as I said, this expression means that this UDL is continued. So that UDL is continued means that this expression means x is going like that way, is continued like that way. Now of course there isn't any. So we need to put an opposite load in this direction. So we need to add this bit of UDL here as well. So again, as simple as that, 10 times x minus 7. So this would be x minus 7. So 10 over 2 x minus 7 square, as we did with this square. So it would be plus 10 times x minus 7 square over 2. Because that would be going upward, so that would come with a negative sign, because that load is going to create a clockwise movement, the bottom load, not the top bit. So the top bit is taken into account here, because that is continuing the trend load there, and this green bit is in there. So let me put that one is a different sign. So this expression, the pink load is given by this expression. So that means the UDL extend from 2 meter till the end. And then the green bit is acting upward, means these two cancels. And finally this 20 is creating an anti-clockwise moment. So that would be final bit of the 20 would be plus 20 times the distance is 2578, so x minus 8 meter. So if you get that expressions over here, now it's fairly easy to do these expressions over here. So you will say EI d2y dx2 is this moment expression. So you integrate it once, so you will say dui dy dx will be first integration of that 50 times x would be 50 times x square over 2. Second integration of that is 91 x minus 2 square over 2. That integration, so 10 over 2, that would be x minus 2 cubed over 6. Minus 29 x minus 7 square over 2. This one minus 10 times x minus 7 cube over 6. And plus 20 over 2 x minus 8 square. So just I have used the expressions from the standard integration. And then finally the deflection you can get, of course that would be integrating constant a. Finally, the displacement you can get 50 over 6 times x cube minus 91 over 6 times x minus 2 cube. And then that would be 4. So 10 over 24 x minus 2 to the power 4. That would be cube. So 29 over 6 x minus 7 cube. And minus that would be 4, 10 over 24 x minus 7 to the power 4, and that would be cube 20 over 6 x minus 8 cube plus ax plus b. So once we have got that bit of information, then you put the boundary conditions as follows. Then you put boundary condition at x equal to 2 meter, y equal to 0. You put that in, and you put at x equal to 7 meter, y equal to 0. So this will give you a and b. Once you get that, put that back in the expression. Now when you are putting x equal to 2, then this will have a value. None of these other will have values at all, because their values would be less than negative values. Is that okay? We are using? Yeah. In this case, if the load does not extend UDL primarily, then you have to put an opposite one, because this expression means the load goes from that point till the end. So that means you put it with the opposite one. If that was a triangular load, you put it in exactly the triangular load opposite way. I cannot hear. Can you combine the brackets of better not to do that? Because one will become x greater than 2, another is x greater than 7. So when you put in the value, if x is more than 2 of 7, the 8, then you can how do we do the triangular load? So if a triangular load was, let's say, from here to here, what you need to do is you need to extend that like this, and similarly then you put in exactly the mirror image opposite way. How do you know that? Yeah, if you know these values, you can find out that value that will give you this, and from the slope you can find out that person. Because this slope is the same as that slope. The slope of the line. Yeah, yeah. Yeah, you come over here. Yes. Okay, so that means that this expression means the load is continuing up to the end. But then we have said that load doesn't continue after this point. So that means we need to put an upward load at the end, so that these two cancel and you get the original condition.
I have a question. Your course. So we have decided to choose this when it is in, when your lift is equal to weight, so it's kind of an equilibrium. But are we wondering, are we allowed, because we found the centre of gravity in your weight effect, are we allowed to just treat the weight as a point load at the centre of gravity?
Yeah. That's for calculating the equilibrium. But when you calculate the bending moment and things, then you have to consider their UDR.
But it doesn't act as actual centre.
No, the weight of the helicopter.
Yeah.
So when you are calculating bending moment for the whole frame, then you have to consider they acting as uniformly distributed or some form of distributed.
Right.
So for equilibrium is fine.
Yeah, when I'm doing bending, why does that change?
Why does it change? Because exactly like this sort of case, when I'm calculating the reaction force, I can take that as a 50 kN moment. But when I'm calculating the bending moment calculation, I have to go back and take the nature of the force as UDL.
Yeah, sure.
Because otherwise the deflection pattern would be different and the stresses would be different.
The thing is, it doesn't, so it
For
doesn't,
equilibrium, that's fine. How much is the forces on the blades and those, that would be fine.
yeah, I've just done that, I've done it for these equations as well.
Yeah.
Like the bending moment.
Yeah. Now then, once you have done the reaction force, take that load and use that distributor.
So it wouldn't change it, it just, I'd have to, it wouldn't change my calculations, it just means I'd have to change it.
So I put something a bit simpler. For this one, basically, I put minus 60.
Send me an email for
I
that
did, I
case.
sent you an email.
When? I
Thing is,
replied
don't
to
know if
everybody.
I sent it to the right one.
So send me another email, and I'll take care of those sort of mistakes. I'll give you marks for those.
Okay, I sent it to this email.
Can you send me again? I've
Is that
almost. Yeah, that's my email. Can you send me again?
Yeah, I will.
Yeah, can you send me
Alright,
again?
cheers.
Because I seems to have not get it.
About the structures course, what's the specific item
Yeah.
we focus on? Can we use objects like the ice skis, like snow skis?
Sorry, I was distracted. Tell me again.
Like objects like snow skis or ice
Yeah,
skates.
yeah. You can. Of course you can.
Alright, thanks.
Of course you can do. So what I'm going to do is I'm going to have a session. Let's see, tomorrow is possibly not, then Monday, where you can discuss your ideas. I'll try to see tomorrow if I can give you a Zoom sessions where you can show me your things and if you've got any queries. And I'll have some of these sessions over the next week so that we can discuss this one. Yeah.
Thank you.
Yeah. Did you not get that one?
Sorry, I was just talking. You know when you write down like you write down the triangular load
Yeah.
from Macaulay brackets. Like how do you write it as a Macaulay bracket?
So exactly, so wherever it starts, so it will start at this point.